Good morning, this is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain general heat conduction in a plane wall, cylinder and a sphere with different type of boundary conditions. Now in general we have this equation actually. This is governing equation in one dimension for any geometry here. So if you want to write for plane wall, just change r equal to x, n equal to 0. For cylinder you can write n equal to 1. For a sphere you can write n equal to 2. So let's do the derivation one by one. General conduction in case of solid block here, so you have a block, differential dimension of that is delta x, delta y, delta z. So heat conduction coming in here is q dot x, leaving here q dot x plus delta x. Here is q dot z plus delta z. This side is qz. Here coming in is q dot y. Here leaving is q dot y plus delta y. Energy generated within the material E dot generation into delta x, delta y, delta z. This is general equations. So rate of heat conduction in at x by z, rate of heat conduction at x plus delta x, x plus y plus delta y, z plus delta z, plus rate of heat generation inside the element equal to rate of energy content change of the element. So by substituting all of them, so here you are getting q dot x plus q dot y plus q dot z minus q dot x plus delta z minus q dot y plus delta z minus q dot z plus delta z, E dot generation within the element plus delta E element upon delta T. Volume of the element is given by this delta x, delta y, delta z. Now energy change of the element is energy at time t plus delta t minus energy at time t. So this is mc t plus delta t minus t at time t. So this is rho c delta x, delta y, delta z t plus delta t minus t at time t. Energy generation within the material E dot generation into volume of the material. So E dot generation delta x, delta y, delta z. Substituting all of them into these equations, arranging them and dividing by delta x, delta y, we are getting these equations. Now in this we are putting here Ax is area in x direction, delta x, delta y. Y direction area is delta x, delta z. Z direction area x, delta y. And now we are putting the limit delta t tends to 0, delta x tends to 0, delta y tends to 0, delta z tends to 0. By putting all that, we are ending up with this equation minus ax del q x upon del x minus ay del q y upon del y minus 1 upon az del q z upon del z plus E dot generation equal to Cp del T upon del T. Now we will use Fourier's law of heat conduction, that is minus k ax dt upon dx. Substitute this here. So substitute that here, that you will get 1 upon ax del upon del x k ax del T upon del x plus 1 upon ay del upon del y k ay del T upon del y plus 1 upon az del upon del z k az del T upon del z plus E dot generation equal to rho c del T upon del T. For constant area, so we can write this equation. So this is general equation actually. Now we can write for constant thermal conductivity. So for that constant thermal conductivity, we can write this equation del square t upon del x square, del square t upon del y square, del square t upon del z square plus E dot generation upon k equal to 1 upon alpha del t upon del t. This is Fourier Wyout equations. For steady state operations, this term is 0, so we have this. This is known as Poisson equation. Poisson equation is del square t upon del x square, del square t upon del y square, del square t upon del z square plus E dot generation upon k equal to 0. Next is transient and no heat generations. So del square t upon del x square plus del square t upon del y square plus del square t upon del z square equal to 1 upon alpha delta t upon t is diffusion equations. Now for steady state, no heat generation, so you have del square t upon del x square plus del square t upon del y square plus del square t upon del z square 0 is known as Laplace equations. So we have derived here Fourier Wyout equations, Poisson equation, diffusion equation and Laplace equation. Now in case of cylinder, just make these changes. X equal to r cos phi, y equal to r sin phi, z equal to z. So you will end up with this equation 1 upon r del r kr del t upon del r plus 1 upon r square del t upon del phi k del t upon del phi plus del upon del z k del t upon del z plus E dot generation equal to rho c del t upon del t. So this is, you can say, differential volume in case of cylinder. In case of sphere, make these changes. X equal to r cos phi sin phi, y equal to r sin phi sin theta, z equal to cos theta. So by putting these changes, you will end up with this equation 1 upon r square del upon del r kr square del t upon del r plus 1 upon r square sin square theta del upon del phi k del t upon del phi plus 1 upon r square sin theta del upon del theta k sin theta del t upon del theta plus E dot generation equal to rho c del t upon del t. Now to solve these we need boundary conditions. So boundary conditions, first is temperatures on outer surfaces at least. So this is called temperature boundary conditions. For one-dimensional problem you need 2 temperatures, for 2-dimensional you need 4, for 3-dimensional you need 6 temperatures. So these are temperature boundary conditions. Now for heat flux boundary conditions, by Fourier's law of heat conductions, the heat flux is given that conduction heat flux is minus k dt upon dx and positive x directions. Sign of heat flux positive in positive direction of coordinate, negative in negative direction of coordinate. For example, a plate of thickness L subjected to heat flux 50 watt per meter square in medium from both sides. So this 50 from this side, 50 from this side. So Q dot is minus K dt 0 upon dx means here. So this is here, plus here, so the plus side. Now at minus side is minus k dt upon dx. So here this is here minus side here, minus 50 at this particular end. At surface L the heat flux is in negative direction, this side. Now we have insulation boundary conditions. So for well insulated surface the insulation is this. So you have here. So here you are maintaining a temperature, you are calculating temperature as a function of x. So insulation boundary conditions, the flux at the insulation point minus k dt upon dx at x equal to 0 equal to 0. So dt upon dx del T upon del x at insulation should be equal to 0. The slope of temperature at the surface should be equal to 0 in order to stop the heat transfer there. Then we have thermal symmetry boundary conditions. So if you say in this particular case, so this is in case of cooling. So here you have highest temperature, this side is low, this side is low temperature. So there is heat flow across, no heat flow across the center plane. So if we have at this particular point here, so del T L upon 2 del x equal to 0. It resembles insulations or zero flux boundary. In case of cylindrical or spherical bodies having thermal symmetry about the center line or midpoint, the thermal symmetry boundary conditions require that first derivative of temperature with respect to R, the radial variable, to be 0. So we say center line, so del T upon the center should be equal to 0. Now next, fifth boundary condition is convection boundary condition. The heat of conduction at surface in a selected direction should be equal to heat of convection at the surface in the same directions. So these are convection boundary conditions. So this is the case here. So this is here some sort of the metal surfaces here. So whatever convection is coming here, same thing will go by conduction. So this x equal to 0. So minus k del T upon del x at x equal to 0 equal to h1 T infinity minus T0 at this side. Now at this end, whatever conduction flux is here, same should be balanced by convection flux this side. So minus k del T upon del x at L should be equal to S2 T infinity minus TL at this side. So H1 and H2 are convection heat transfer coefficient, and T infinity and T infinity 2 are surrounding temperatures. Next is radiation boundary conditions. So heat conduction at the surface in a selected direction should be equal to radiation exchange at the surface in the same directions. So if we say this is the here, all the radiation coming in at this particular surface should be balanced by conduction flux here. So this is here is epsilon sigma 1 T surrounding 4 minus T0 4 should be equal to minus k del T upon del x at x equal to 0. At this particular point, if this is leaving to this side, so minus k del T upon del x at L should be equal to epsilon sigma TL to the power 4 minus T infinite T surface square. So this is in this side. So epsilon 1 and epsilon 2 are the emissivities of the boundary surfaces. So sigma is Stephen-Boltzmann constant given by this 5.67 10 to the power minus 8 watt per meter square per Kelvin 4, and T must be in Kelvin only. Now next is interface boundary conditions. So for the interface, if you have an interface part here, so this is interface, one is material A, one is material B. So now see the temperature profile is a continuous function actually. So that is the perfect conditions for interface. So now what you have here, the two bodies in contact must have same temperature at the area of contact. Means this particular point, this material and this materials have the same temperature. At the interface, which is a surface, cannot store any energy, and thus heat flux at the two sides of the interface must be same. It means whatever heat flux is coming from A to the interface, same is being transferred to the B, because the interface cannot store any amount of energy within it. So you have two conditions here. The temperature at the interface of both materials should be same. So TA at x equal to 0 should be equal to TB at x equal to 0. Next is whatever flux is coming to the interfaces are equal. So minus K del TA upon del x at x equal to 0 equal to minus KB del TB upon del x at x equal to 0. So at this particular point, all flux, the conduction fluxes must be equal. Now, generalized boundary condition, we can say the heat transfer to the surface in all modes are equal to heat transfer from the surface in all modes. So whatever coming in from all modes should be balanced by whatever going out in all modes. Now here we will solve one problem for each case. So this is a problem statement. Consider a base plate of 1200 watt household iron that has a thickness of L 0.5 centimeter. Base area is 300 centimeter square and thermal conductivity K equal to 15 watt per meter per degree Celsius. The inner surface of the base plate is subjected to uniform heat flux generated by resistance heaters inside, and outside surface loses heat to the surroundings at T infinity equal to 20 degrees Celsius by convection, taking the convection heat transfer coefficient to be at 80 watt per meter square per degree Celsius, and disregarding heat loss by radiation, obtain an expression for variation of temperature in base plate and evaluate the temperatures at the inner and outer surfaces. So we are making these assumptions. First, the heat transfer is steady since there is no change with time. Heat transfer is one-dimensional since surface area of base plate is large relative to its thickness, and thermal conditions on both sides are uniform. Thermal conductivity is constant. There is no heat generation in the medium. Heat transfer by radiation is negligible. Upper part of the iron is well insulated so that the entire heat generated in resistance wire is transferred to the base plate through its inner surface. So if you draw the figure, this will look like a plain wall. So here you have a plain wall of thickness L. This side is actually the electrical heater in case of press, where you are generating some constant flux by the electrical heating here, that is Q naught. Now that flux is being transferred to the base plate by means of conductions. So that is balancing by conduction flux here. Now at the bottom of the plates, the plate will lose energy to the surrounding air by means of convection, which is given by this as TL minus T infinity. So since the inner surface of the plate is subject to uniform heat flux, that is Q naught Q dot upon area of base, so you can calculate here the heat flux 40,000 watt per meter square. Taking direction of heat flow normal to the base plate, so you have this is the equation that need to be solved. D square T upon dx square equal to 0. This is governing equation under steady state. operation totally in one-dimensional case for constant thermal conductivity without heat generation within the material. So the boundary conditions are that minus k dt upon dx at x equal to 0 equal to q naught equal to 40,000. Now that flux at x equal to L minus k dt upon dx at L equal to h TL minus T infinity. So we can integrate that, you will get C1, then again integrate it C2. So at x equal to 0, so if we will put at x equal to 0 here this flux, so at x equal to 0 you will get this actually your C2. So at x equal to 0, so this here to dt upon dx should be equal to C1. So here minus k dt upon dx is this minus C1k, so q naught equal to minus k C1. So C1 is minus q naught upon k. Now second condition that k dtl upon this HTL minus this, so k C1 H C1L plus C2. So this is from temperature expression. So from here the TL is C1L plus C2. So C1 is this. So we can put the expression of C1 here. Then we will put the expression of C1. Then we will find the expression of C2 is T infinity plus Q naught upon H plus Q naught L upon K. Substitute them back, you will get your expression for Tx is C1x plus C2 is minus Q naught x upon K plus T infinity plus Q naught upon H plus Q naught upon K into L. So we can rearrange it, so you will get Tx equal to T infinity plus Q naught L minus x upon k plus 1 upon h. Now we can substitute the values from our given questions. So x equal to 0 we are calculating at the inner side of the base plate. Temperature is coming here 533. Surface temperatures by putting conditions here we are getting here 520. So another example for plane wall is that you have plane wall thickness 8.06 meter, thermal conductivity K is 1.2 watt per meter per degree Celsius. The wall is covered with white porcelain tiles that have an emissivity of 0.85 and solar absorptivity alpha equal to 0.26. The inner surface of the wall is maintained at T1 equal to 300 Kelvin at all times, while the outer surfaces are exposed to solar radiation that is incident at the rate of Q dot solar equal to 800 watt per meter square. The outer surface also losing heat by radiation to deep space at 0 Kelvin. Determine the temperature of the outer surface of the wall and the rate of heat transfer through the wall by steady operating conditions are reached. What would be your response be if no solar radiation was incident on the surface? So this is a schematic of that. This is plane wall. This is maintained at temperature T1 here, and by means of conduction it will here at this particular point. So you have a conduction flux due to this side. Now from here sun, it will have solar energy, it will absorb something incident, some component, and this surface will also emit the energy in the form of the radiation, so which will go outside actually. we have the emissivity and absorptivity, so both need to be encountered. So assumptions are: heat transfer is steady since there is no change with time. Heat transfer is one-dimensional since the wall is large relative to its thickness, and thermal conditions on both sides are uniform. Thermal conductivity is constant, there is no heat generation. So in that case, our governing equation is d square t upon dx square, d square t upon dy square, d square t upon dz square plus E dot generation upon k equal to 1 upon alpha del t upon del t. Now purely for one dimensional, so your y dimensional term, z dimensionals are 0. No generation, this term is 0. Steady state operation, this term is also 0. So this is the equation you need to solve all the time under steady state, one dimensional and without energy generation within the material. D square t upon dx square equal to 0. Boundary conditions are at T equal to 0, temperature T1 is 300 Kelvin, T equal to L, conduction flux K dt upon dx at L would be balanced by this. So first is energy, what is coming to the surface actually by this, and some component of this is actually this is the energy loss from the surface. So epsilon sigma TL4 minus T4 space. This is what you have, the energy is being absorbed from the solar energy, so Q dot solar multiplied by alpha. T space is 0, so you have T is actually C1x plus C2. So from here you can find that x equal to 0, so your T1, so you find C2 equal to T1. Now dt upon dx is equal to your C1, so you can find TL C1L plus C2. Substitute that here, TL here, so TL here at this particular point, K1 C1 here, substitute here. Let the surrounding temperature TL instead of TL equal to TL C1L plus T1. So in that case we can write here this one, that TL sigma epsilon TL4 minus alpha Q dot solar actually. So K here, now you can arrange here, so you get C1 equal to alpha Q dot solar minus sigma epsilon TL4 upon K. Now substituting C1 C2 in equation back, so your Tx equal to alpha Q dot solar minus epsilon sigma TL4 upon Kx plus T1. So at x equal to L, TL equal to TL. So you will find at x equal to L, so you have TL equal to alpha Q dot solar minus epsilon sigma TL4 upon KL plus T1. This can be solved by any nonlinear equation here, nonlinear equation solver. So by substituting that you will get all these equations. So this is the equation in terms of TL. You can solve by non-linear equation solver or by trial and error methods. So in that case TL comes out to be 292.7 Kelvin. Now you know the TL, so you can substitute there. So you find the expression for Tx is minus 121 Kx upon M, minus 121x plus 300 actually. So your Q dot is rate of heat conductions is minus K1 C1, so that is 146 watt per meter square. Now consider so in previous case, in case of absence of solar radiation, what will change? So in case of solar radiation, only this alpha term would become 0. So this term will vanish, and then you can do the rest of the calculation same thing. Now let's say the next case in the cylindrical coordinate. Cylindrical coordinate, let's say we have a steam pipe of length L, 20 meter, inner radius is 6 centimeter, outer radius is 8 centimeter. Thermal conductivity K is 20 watt per meter per degree Celsius. Inner and outer surfaces of the pipes are maintained at average temperatures T1 equal to 150 degrees Celsius, T2 equal to 60 degrees Celsius respectively. Obtain a general relation for temperature distribution inside the pipe under steady conditions and determine the rate of heat loss from the steam pipe. Now here this is what you have here. So steam is being filled here. The pipe of inner radius R1, outer radius R2, and we have some material thickness. We want to calculate what is the rate of energy loss from steam to the pipe. So this is general equations for and heat transfer in radial directions only in case of without any energy generation within the material under steady state of operations. So boundary conditions are at R equal to R1, temperature T1 is 150, at R equal to R2, temperature T2 equal to 60 degrees Celsius. So we can integrate that. So if you integrate that, you will get T1 equal to C1 ln R plus C2. These two boundary conditions, substitute them one by one, you can calculate constant C1 and C2. So first we are not substituting values, we are substituting in terms of variables. So in that case, first equation is this, second equation is this, we can solve them simultaneously. So from here we got C1 equal to T2 minus T1 upon ln R2 upon R1. Substitute this into equation number 1. We will end up with C2 T1 minus T2 minus T1 upon ln R2 upon R1 into ln R1. Now C1 upon C2 can be substituted in main equations of temperature action, C1 ln R plus C2. So substitute the values here, arrange them, then we will end up with TR equal to T1 plus T2 minus T1 upon ln R2 upon R1 multiplied by ln R upon R1. Rate of heat loss from steam is total rate of heat conduction through the pipes. So Q cylinder is minus Ka dt upon dr. So dt upon dr is C1 upon R. So this we are calculating at R equal to R1. So that you have here that so this can be cancelled, R is R cancelled, so 2 pi KL into C1, so C1 is given by this. The Q cylinder is 2 pi KL T1 minus T2 ln R2 minus R2 upon R1, substitute that value, 786 kilowatt. Note, total rate of heat transfer through a pipe is constant, but heat flux Q dot is Q upon 2 pi RL is not, since it decreases in the direction of heat transfer with increasing radius. Now another example, we are considering here the heat transfer in a spherical coordinate. Consider a spherical cylinder of radius R1 equal to 8 cm, outer radius R2 equal to 10 cm, and thermal conductivity K equal to 40 watt per meter per degree Celsius. The inner and outer surfaces of the container are maintained at constant temperature T1 and T2 at 280 degrees Celsius respectively. As a result of some chemical reaction occurring inside, obtain a general relations for temperature distribution inside the cell under steady conditions and determine the rate of heat loss from the container. So heat transfer in steady state, this is the sphere of inner radius R1, outer radius R2. Somehow you are maintaining this at a fixed temperature 200 degrees Celsius and this temperature at 80 degrees Celsius. We are supposed to find temperature distribution within the wall of the sphere. So here we are considering heat transfer in steady. Since there is no change with time, heat transfer is one-dimensional since there is thermal symmetry about the midpoint. Thermal conductivity is constant and no heat generation within the material. So in this material, no heat generation actually. For that case, our governing equation is d upon dr r square dt upon dr equal to 0. Two boundary conditions at T equal to T1 at R equal to R1 at R equal to R2, T2 equal to 80 degrees Celsius. So by integrating that, we will get our governing equation would become this: T equal to C1 upon R plus C2. Substitute the boundary conditions in terms of variable there. You will get C1 equal to minus R1 R2 upon R2 minus R1 bracket T1 minus T2. Substitute this into equation number 1, 2. So here T1 equal to R1 R2 upon R1 R2 minus R1 T1 minus T2 plus C2. So C2 comes out to be R2 T2 minus R1 T1 upon R2 minus R1. Now temperature is minus C1 upon R plus C2. Substitute the constant C1 and C2. So your temperature equation is R1 R2 T1 minus T2 divided by R2 minus R1 multiplied by 1 upon R plus R2 T2 minus R1 T1 divided by R2 minus R1. Now heat transfer rate to the sphere is minus k dt upon dr. So from here A is 4 pi square C1 upon R square this. So this is independent of R, heat transfer rate. So minus 4 pi k C1. So C1 expression can be substituted here. So Q dot heat transfer rate in case of the sphere comes out to be 4 pi k R1 R2 T1 minus T2 upon R2 minus R1. Substitute the values, you will get expression is means 27.1 kilowatt. So these are the references we have from Sangel. One is heat and mass transfer, a practical approach. The other one is fundamentals and applications. So thank you. In case of doubt, you can drop your comment. We will answer it. Thank you very much.